I'm Antonio Sala, and in this video we are going to model this rack-and-pinion mechanism by using Lagrangian and Euler-Lagrange equations. We'll do it in various ways to check that the result is equivalent and coincides with the previous video in which we obtained the equations of motion by means of Newton equations, force and torque balances. These are the notation elements we are going to consider. The linear displacement of the green mass will be denoted as Q2. The angular displacement of the pinion will be denoted as Q1. There will be an exogenous force F that, when positive, will mean that it's pushing to the left, and there will be a torque tau exerted on a fixed rotation axis which will try to move the pinion, and vertical displacements will be locked. Just some things here holding this in place, and of course there will be some contact reaction force that, well, as we are not dealing with the intricacies of the teeth shape, we will just consider that contact is made at a fixed distance rho from the center of rotation. So this will be simplified to a cylinder rolling on a plane, let's say. So the basic idea perhaps that comes to our mind is that, well, this is not a 2-degree of freedom system, because, okay, Q2 is rho times Q1. So the system is not as complex as it appears with so many letters. We'll exploit that fact, of course. So let us go with the Euler-Lagrange equations. There is something called Lagrangian, which is kinetic minus potential energy, and in this case, as there are no springs storing potential elastic energy and there is no vertical movement against the gravitational field, so no potential gravitational energy, then V potential energy is 0, and the kinetic energy, capital T, will be 1/2 of mass times velocity squared, Q dot 2 squared, plus 1/2 moment of inertia times angular velocity squared, Q1 dot squared. So this is the Lagrangian. Then Euler-Lagrange equations tell me that for each generalized coordinate, Q1, Q2, or, well, we'll see later on, we'll have some generalized momentum, partial of L, partial velocity I, and that the time derivative of that momentum is equal to the partial of the Lagrangian with respect to positions plus some exogenous term which will be computed with the virtual work these exogenous forces do when coordinate moves. More on that later. So, well, this would be the idea, but these equations are only valid for unconstrained motion. So we will first substitute the constraint in here to have just 1 degree of freedom, one letter in the Lagrangian, and apply the unconstrained equations, and later on we will modify this Euler-Lagrange stuff to incorporate constraints. But let us first do it the easy way, which is realizing that, okay, come on, I don't need 2 letters in here because Q2 is just proportional to Q1. So if I express L as 1/2 m rho dot Q1 squared, because, okay, of course, this implies this, plus 1/2 moment of inertia times, again, dot Q1 squared, then I have just 1 letter in the Lagrangian, so I need to apply this Euler-Lagrange equations just once. I will have P1 equal to the partial of this with respect to the velocity, which will be carrying out operations 2 in the square when taking derivatives will cancel the 1/2, and I will have m rho squared plus I times q1 dot. So this will be the generalized momentum as seen from the movement of q1, and in fact q1 is an angular velocity, angular momentum is inertia times angular velocity, so this is an equivalent inertia. Good. The thing is that the time derivative of p1, in order to apply this, will be equivalent inertia times acceleration, and that will be phi, because the Lagrangian does not depend on position, so this will be 0. In our particular case, of course, with springs or vertical movements that would no longer be true, but in here this is 0. And then phi is computed as follows. When q1 has a virtual displacement delta q1, then the work will be, well, torque times angular displacement plus force times linear displacement, in this case not plus but minus because of these opposing directions. And of course, as delta q2 is rho delta q1 from the kinematic constraint, then this means that in the right hand side I will have tau minus f rho. With this we obtain the equation of movement in the q1 coordinate, which is equivalent inertia times acceleration equal to some torque balance. So this is it. Tau and f are exogenous input assumed to be known, then I can solve these differential equations for q1 by computing accelerations and integrating them to give me velocities and position. So good, this is the reduced equation to the angular coordinate. However, instead of replacing q2 as a function of q1, I could have also used that q1 is q2 divided by rho, and so with the speeds, so I can get an alternate but equivalent form of the Lagrangian with just looking at here, letting q2 unchanged and replacing this velocity by q2 speed divided by rho, inertia divided by rho squared times q2 dot velocity squared. So indeed, with that Lagrangian, which I will summarize to these expressions, then I will have the momentum in the second coordinate. It will be this equivalent mass times linear velocity, so its time derivative will be equivalent mass times linear acceleration, and that will be a force balance that I will express with some virtual work considerations, which in this case will end up being tau times 1 over rho minus f delta q2. So it means that this expression that multiplies the virtual displacement is the one that goes in the Euler-Lagrange equations. And this is it. This is the Euler-Lagrange equation in terms of the linear coordinate with equivalent mass times acceleration, some force balance, in which I divided torques by radius to have force dimensions. So these two equations are equivalent. I don't need both. I can express my movement in the angular coordinate and then multiply by the radius to get q2, or I can express my movement in the linear coordinate and then divide by radius to get q1. So I need to solve just one of these equivalent ordinary differential equations. Good. Now we will do it in a third way, which will be with the constrained Euler-Lagrange equations. as follows. We will now write the equations without eliminating q1 and q2. It's much easier if I eliminate one of the variables at start, but okay, it's an equivalent way of doing it. So the thing is that if I am going to use these partial derivatives with respect to q1 and q2, the constraint will be incorporated by defining a new Lagrangian, I will call it Lagrangian tilde, which is the original one, plus some Lagrange multiplier times fq, where fq is a way of expressing the constraint, so fq must be 0. In our case, my constraint will be rho q1 minus q2 equals 0, so incorporating this stuff to the Lagrangian and doing the Euler-Lagrange equations with this tilde L, then I will obtain the constraint movement equations, and lambda will be another way of saying that there are reaction forces, as we will discuss later on. So at the end, if I just put here the tilde and do the derivatives, I will get the same equations as before, but adding, when I have this tilde, I will have to take derivatives of this with respect to q, so I will have the original ones plus the Lagrange multiplier times the partial derivative of the constraint. Well, that's it, so let's do it. Now I need to express these things twice, not just once, as we did before when just eliminating one of the coordinates. Now I need to write p1, which is the partial of this with respect to q1 dot, which will be inertia times angular speed, and then p1 dot, which is inertia times acceleration, will be equal to the exogenous force term, which in this case will only involve tau, because F does work against Q2 but not against Q1, and then I must add the constraint related plus lambda times the derivative of F with respect to Q1, which is rho. Then we have the acceleration Q1 fulfilling this equation, but contrarily to what happened before with substitution. In here I have two unknowns and one equation, so the model is not complete. Indeed, I need further equations with P2, partial of this stuff with respect to Q2 dot, which will be mass times linear speed, and then its time derivative, P2 dot equal mass times acceleration of Q2 equal to exogenous terms, which in this case is minus F. Tau does not do work on Q2, not directly. Of course, it will be via reaction forces. We'll discuss that in a minute. But it does not appear here, and what we have is the Lagrange multiplier plus lambda times the partial derivative of the constraint with respect to Q2, which in this case is minus 1, and then we have a second equation of movement, 1, 2, plus the constraint 3, and this is already a complete mathematical model because we have Q1, Q2, and lambda as 3 unknowns. So with suitable manipulations, we will be able to solve this system of algebraic differential equations to get Q1, Q2, and lambda. Of course, I mean, we can in here substitute, replace, and do whatever manipulations we wish. And indeed, we have already done that in a previous video in which we consider reaction forces. Because if you see what is the role of lambda, the thing is that if F has units of, in this case, linear displacement, then this lambda has dimensions of force, because indeed, look that if we were doing the Newton equations of the green mass, we will have minus F plus R, so it means that lambda should be minus the reaction force. So I would get plus reaction force in this linear movement equation. And then if I did the torque balance in the pinion, then this reaction force changing sign will exert a torque of minus R times rho, force times distance, and indeed that also is consistent with lambda being the inverse of the reaction force. So basically the Lagrange multiplier is the reaction force. So we started with Euler-Lagrange and we ended up with something which is exactly the same as the Newton force and torque balances. And if you watch the previous video in which we manipulated these three equations, we ended up getting the reduction to Q1 and the reduction to Q2. So these three equations are equivalent to those two alternate ways of expressing the equations of movement. So we'll end up here. In this video, we have discussed three different ways of expressing the equations of movement of this pinion-rack mechanism using Euler-Lagrange formalism. Two of them with 1 degree of freedom unconstrained versions, expressing the Lagrangian only as a function of Q1 or only as a function of Q2, and a third way in which we kept the Lagrangian as a function of Q1 and Q2, and we introduced this kinematic constraint via a Lagrange multiplier, so we ended up with three equations and three unknowns. All three ways of expressing the equations of motion are equivalent, so depending on the situation, you can decide which one to apply. Well, we end here. Thanks for watching.